Take a look at this right here. That thing right there lives inside of this square root, right? So this would be composition also. Here's something else. How about tangent to the fifth of x sine x? All right, we've got a lot going on here. Do we have a product? Yes. I do see a product. I see a product right here, right? But the problem is that product lives where? Inside of a tangent function. And then this fifth power means we're raising the whole thing to the fifth power. So this again is composition. And in one of the first classes we had, right, one of the first days in this class, we actually did some of these problems where I put something like this up on the board, and what we had to do is break it down into smaller functions. Do y'all remember that? Probably it's been a while, but I told you all to basically, start from the outside and say, what's the last thing that would happen here? So, like, what would be the last thing that happens? If you start plugging in x, what would be the last thing happening? Fifth power. What would be the thing before that? Tangent. And then before that would be you have to figure out what that is, right? Do y'all remember doing that in the very beginning? Okay, it's back. Okay, it's going to be back today. So all of these functions right here that I put on the board, right now you cannot take the derivative of unless you know the chain rule already. All right? So we have to have a rule that allows us to deal with this. Okay, so here's how the chain rule works. Chain rule says this. Let's start out with just the basic idea that let's say we have some function. Let's call it, y is equal to some function composed with some other function. That's the notation from college algebra, right? F of g of x. But what that really means is f, and inside of f is the g function, right? That's what that notation means. So like in this particular case, this is the composition of two functions. Would you agree? What would be f and what would be g? Sine of x. Sine is the outer function, so that's f, and then the g function would be this piece, yes? Okay. These two are a little more complicated. This is like triple composition. This is like a function and a function and a function. So there's like 3 layers to it. So let's say we have this, right? So given a composition like this, y is some function of x, or sorry, y is the composition of f and g together, then the derivative of this is equal to the derivative of f at g of x times the derivative of g of x. That's it. That's the chain rule right there. This is it. The problem is students have trouble understanding how to implement the formula. So let me first verbally say what's happening, and then we'll try and do an example. So it says that if you want to take the derivative of composition, what you have to do is first look at the outer function, all right, f. You need to take the derivative of that function. But inside of it, you don't put x, you put what? You put the function g, but with no derivative. You don't want to touch it. Just you take the derivative of f, but plug into it g. After you do that, you multiply by what? The derivative of that piece that was inside, the g. Okay, so let's go to this example right here. Actually, I'm going to erase this and just start right there. I'm going to call this y, and let's see if we can apply this rule. Okay, so what is our f function here, and what is our g function? So the f function is the outer one, which you said was sine x, and then the inner function g is the x squared plus 1. You okay with that? Like back in college algebra, that would be something that you could be asked. Take this, take these two, compose them, and you get that, right? We should be able to now go from there back to this. Now if we do that, we can take the derivatives of each of these, can't we? Okay, so what would the derivative of this be, just by itself? What's the derivative of that function? Cosine x. Okay, what would the derivative of this function be? 2x, and that's it, right? Okay, now according to the chain rule, the derivative of this function up here should be equal to the derivative of f, which is what? Cosine x, but don't plug x in. Plug what? Plug g into it, right? So I'm supposed to take cosine x, but plug g into it. So I'm supposed to take cosine and put into it not x, but what? X squared plus 1. And that takes care of this piece right here. And then I multiply that by what? The derivative of g, which I have right here, is just 2x times 2x. What do y'all think? Now, I could clean this up a little bit, okay? So one thing I could do is I take that 2x, and I can't put it in here, right? Please do not do that. I can bring it out front, though. 2x cosine of x squared plus 1. And that just looks more like what you would see in the textbook. Let's do another one, all right? Let's do another one. And then, well, we'll see how y'all do with this. Next one. How about this? X to the 4th plus 3x squared plus 1 to the 100th power. Now, if you did not have the chain rule, the only way you could do this problem would be to multiply this times itself 100 times and do all the distribution, right? Would that be fun? Y'all understand what I'm saying by that? So I don't feel like doing that. And if you did, if you're like, I could do it, I would just make that like 100,000, and then I think I could make you submit at some point, right? But is this composition? It is. You have a function inside of a function. So what you need to now ask is like, what's the outer function? So what's the last thing happening? Something is being raised to the 100th power, right? So I'm going to call that f, my f function. That's the something being raised to the 100th power, so that's x to the 100th power. And then what's the g function inside of that? It's the polynomial x to the 4th plus 3x squared plus 1, right? Omar, do you understand?
Yes.
Jesse, you understand? James? Oh, James, oh. Smiley face, frown.
Yeah.
Do you all understand? Okay. So now what? What should I do? Just take derivatives of each of those. Okay, so let's take derivative. Derivative of this is 100 x to the 99. Okay. And then the derivative of this one is 4x cubed plus 3x squared plus 1, right? No, not plus what? What am I doing? What? That was like a total meltdown or something there. Okay. All right, now we apply this. Yes?
So in this case, the f of x is the exponent of 100?
Yes, because it's the last thing to happen. So like if I asked you to plug in 2 here, right? You do 2 here, do all that, get all that number, and then the last thing you do is raise it to the 100th power. So the 100th power is the outer function, and so that's the f. And then the function on the inside, which is the base right here, this thing right here, is going to be our inner function, which is g. And when you set this up, when you figure out what f and g are, you need to be able to take their derivatives, don't you? And I'm comfortable taking derivative of that and this separately, right? All right, so now the answer. the derivative of this should be f prime, right? But not with x plugged in, with what plugged in? G, and G is all this, right? Okay, so it's 100, and then in parentheses, x to the fourth plus 3x squared plus 1, but all of that raised to the 99th power, and then times what? G prime of x, which is just the 4x cubed plus 6x. And that, on the test, would not be right. Why? I have to have parentheses on this. I have to. It's not because I like parentheses and I just love drawing them. It's that if you don't have this, right, then you're really saying it's all of this crap times that, right? Then plus 6x. But it's everything over here. So if you ever wanted to clean this up, you would have to multiply like all of this to the 4x cubed and then all of this to the 6x. You'd have to distribute it, right? So that parentheses has to be there. Okay? This is the derivative. There it is. All right? Questions? Let's try another one. It's almost fun. It's almost fun. Uh-oh. Yes?
So the way to remember how to split your f of x is like just remember that f of x is something that you're always doing last, and then your g of x is what you're doing first, right?
Yeah, so we want to be comfortable with the idea that when we look at the composition of functions, we always want to try and identify like an outer function, and that'll be our f, and then the inner function would be our g. Is that what you're asking me? But here's the problem with that. There's nothing that says that the problems we have to be a composition of just two functions. Like what if we have a composition of 5 functions? Then you're going to have an outer layer, an inner, and we haven't done that yet, but we're headed there. Stay tuned. So I don't want you to I don't want to lock you into a mindset of we're always going to have just 2 functions. I don't want to lock that in yet. I want you to think a bit more abstractly than that. Right? Outer, we're going to work from the outside in, but just let's one foot in front of the other first, all right? So look at this one here. Do you see composition? Do you see an outer function and an inner function? All right. So I'm still sticking to 2 functions right now. What would be f and what would be g? And let me call on somebody. Because everyone said, yeah, I got it. No problem. Marcus. All right, Marcus. So do you see an outer function?
Yes.
What do you got?
Square root.
Square root function. So square root of x. Everyone good? Okay, and then what is your inner function then?
X over x squared.
Okay, x over x squared plus 1. Now, Marcus, I said something a second ago. I said if you're going to call, something f and something g, you better be able to take the derivatives of those, right? Are you going to be okay taking derivative of that?
Yes.
Okay, what about this?
Yes.
What are you going to use? Quotient rule. See, even though this is just an inner function, to take its derivative, I'm going to have to pull the quotient rule out. Can we do it? Yes, but it's going to be some work, right? So let's go ahead and take our derivatives now. So derivative of square root of x is 1 over 2 root x. And I did tell everyone to just memorize that one, right? Okay. And then this one, okay, that derivative so what we have to do is we have to kind of imagine that we've had an entire weekend to absorb the quotient rule. And we have. So I would expect now that you can get from, take this derivative, not necessarily like do it in your head and get the answer, but at least be able to write it out without having to pull out formulas. And so I'm going to do derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. So notice I'm actually not writing the prime marks anymore. I'm just actually doing the derivatives in my head. Right? Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Quotient rule. Derivative of the top times bottom minus blah, 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 blah. Yes? Now, some of you may have learned this. Some people have seen calculus in high school. Has anyone heard of this thing like Lodi high minus Heidi low or something like that? Al, what is it? Heidi low, Lodi high?
I don't want to mess up my mind right
Yeah, I don't either. So there's like a cute little like jingle that you can sing. It's like, wait, hold on. Like, would y'all agree that this is the high function? It's up top, and this is the low function. So you could say like low d high, derivative of the high one. Lodi high minus Heidi low over low square. I don't know, but there's a little jingle. I don't teach jingles, okay? But I just always remember derivative of the top times the bottom minus the derivative of the bottom times the top. It's just all like waking up in the middle of the night like Kill Bill, all right? All right, clean this up. X squared plus 1 minus 2x squared, which leaves us with, I believe, just 1 minus x squared, all over x squared plus 1 squared. Right, the top is x squared plus 1 minus 2x squared. Okay. Luke. How's it going, Luke? You ready to give me the derivative? Okay, let's do it. So y prime should be, so what's this part right here going to be for us?
1 over 2.
Okay, 1 over 2
And then you put
square root of
x over x squared.
x over x squared plus 1, right? So what he's done is he's used the derivative function, but instead of plugging x into it, he plugged in the g function, wherever x was in here, right? Perfect. Keep going, Luke. Times
And then the g.
g prime, which is the 1 minus x squared over x squared plus 1 squared. It's ugly, but that's it. That's our derivative. Good. Yeah, so I was just going to mention, like for right now, for today, let's just take the derivatives, okay? Let's not spend time trying to clean these up right now. Let's just make sure that we got the mechanics down, because at this point, it's algebra, right? So we'll don't worry, we'll be tested in our algebra within the homework and stuff like that, but I don't want us to get bogged down with the algebra, because this is going to get much more complicated, all right? So we got to make sure we can get through the calculus part. Okay. Now, I'm contemplating something right now. The first example I gave you was y was sine of x squared plus 1. Was that the first one we did? Sine of x squared plus 1. Okay, what was the second example I gave you? Oh, was that the x to the 4th plus 3x squared plus 1 to the 100th? And then the one we just did was y is equal to the square root of x over x squared plus 1? Okay, those are the three problems we just did, right? And from what I could tell, you seem to follow it, breaking it down, f and g, take the derivatives, and then just use the formula, right? If I were to go down the hall into a Cal 2 class and pull a Cal 2 student out and bring them in here and ask them to take a derivative of one of these, they would have no idea how to do it. No, I'm just kidding. Hopefully they would. They would not do what I'm showing you to do right now. They would not write down what f and g are, then make a little derivatives of each one, and then use they wouldn't do that. They're going to do a majority of the work up here. So let me show you these three problems again. The shorter way and the way that you want to start heading towards. It's not going to happen necessarily day 1. Maybe it's not going to happen day 10. But by the end of the semester, well, no, I mean, sooner than that, you want to start thinking about these this way, all right? So what I'm going to be using is this idea right here, this power rule. That's basically what I'm going to be trying to tap into here. And just the idea that we know the derivatives of certain things, right? Something to a power, we know the derivative. Sine of, derivative sine, we know. Derivative square root, we know. So this is where things get a little silly. So what I'm going to do is I'm going to ask you, if you look at this as composition, if we were just to replace this x squared plus 1 with my mouse, and I ask you, what is the derivative of a mouse? You're going to say to me, it's cosine of a mouse, right? Do you all agree with that? Okay, so the derivative of this should be cosine of the mouse. Now, that's almost what the chain rule is saying, but the chain rule says once you do that, okay, once you replace the mouse in here, you still have one more thing to do. You have to multiply by whatever the mouse was, the derivative of it. So what is the derivative of this? 2x. And if you check, that's the same answer we just got a second ago. Let me do it again. Derivative of sine of a mouse is cosine of the mouse times the derivative of the mouse. How about this one? Need something a little bigger. I would say this is dirty rag, but it's brand new. It's just barely used. So what if you have this rag to the 100th power? What would be the derivative of a rag to the 100th power? It would be 100 the rag to the 99, right? Okay, the rag is what? X to the 4th plus 3x squared plus 1. But we're not done. Because this was composition, we have to say times. Now, we take the rag, we peel it off, and we say what was there? And we take derivative of that. So derivative of that is tacked on here. 4x cubed plus 6x, right? And that's the answer we had from earlier. Okay, here, I'll bring something out. A folder, yes, a folder. What is the derivative of the square root of a folder? The derivative of the square root of a folder is 1 over 2 roots of the folder. Okay, the folder is this. But then chain rule says you must multiply that by the derivative of what that folder was, which would require some quotient rule. So you go do the quotient rule on the side, and you come up with 1 minus x squared over x squared plus 1 squared. So maybe that would take a little work, right? This maybe the quotient rule we can't do in our head, but this part we could, right? Do y'all see how that works? You sure? Okay. So if you really see how that works, let's see if we can do a couple more. Now you can always fall back on what I started class with the f and the g and then making your little derivatives. But let's see if we can't really push this. Let's take this one. Are you all ready? We're going to take the derivative of this. Is it composition? Okay, how many layers to this composition? How many functions do we have? There's 3. What's the outer thing, the last thing to happen? Cubed. What's going to happen before that? Sine. And what's inside of that? This right here. Okay? So really, if it helps you, you could rewrite this way. If that helps you, that's the same thing, right? That's what that cubed means. And so now, I might have to break out my arm here. Yes, it's going to be my arm. The derivative of this is, well, it's my arm to the 3rd power, right? And what's the derivative of my arm to the 3rd power? 3 arms to the squared, right? So that's going to be 3. What was my arm? All of that, right? Sine of x squared plus tangent x. All of that what? Squared, right? So that was my arm to the 3rd power. The derivative of that is 3 times my arm to the 2nd power. Now, I'm not done, right? I'm not done. times. Now what do I do next? What do you think I do next? I need to go to the middle now. So I've already taken care of the third power, right? I've already taken care of that. So now I'm going to go to the next layer. The next layer is the sine part, right? So now I can go back to this rag. Now I have sine of a rag. So what's the derivative of sine of the rag? Cosine of the rag. So I put cosine of what? X squared plus tangent x. And I close off the cosine there, right? Am I done? No, because I still had something inside that sine, right? The rag was covering something up. So I say times again, and now I go inside, right? This was my rag. I uncover it. I take derivative of this. And that doesn't require any product rule, any quotient rule. It's just we can take the derivative of that. So derivative of this is 2x plus secant squared x. Now I'm done. No, I'm not. Has to be in parentheses. You have more than one term here, right? It's multiplied. You have to have that in parentheses. This is your derivative.
What was the last one? Derivative of again?
Was the inside. Okay? So there were 3 layers to this, right? 3 layers. You had the cubed, and then the sine, and then the junk inside. So we start with taking derivative of the cube part, then the derivative of the sine part, then the derivative of the inner part. All chained together, right? Chained together. Chain rule. Okay, I want to stay within the context of the book. I'm known to go quite off the rails with problems like these, so.
Can we do y equal to x secant kx?
Secant what?
X secant kx?
Where?
Number 15 out of 2.525.
Yeah, I'll do something similar to it. Okay, this one's a little tricky. Ian? Where's Ian? No Ian? Annika? Right? Yes? Okay. So, what do you see here? I thought I heard you say it. There's a product. There is a product. Does everyone see that product? It's right here. Okay? Keep going. I think you were going to say something else, though. And then this right here by itself is composition. This is actually an outer function secant and an inner function 4x. Do y'all see that? So what do you do if you take the derivative? I mean, you have a product, but you also have composition. Everything I've given us up to this point has been just purely composition, composition, composition. Here I'm mixing it up. So the way we do this, do you have an idea of how to do this? It's okay if you don't. I mean, just let me help you. Why don't we try the product rule first? Right? Let's just go with the product rule. What would the product rule tell you you need to do here? So derivative of x times what? Times secant of 4x, and then what? Plus the derivative of secant of 4x, right? Times x. Does everyone agree that that makes the most sense? We have a product, so we apply the product rule. Now, do you see that when you take derivative of this, no problem, right? 1 times that. But when you get to this, you actually have to use the chain rule because you have secant of 4x. So you have to do a little composition here. So let's do it, okay? Derivative of that, said it was 1, right? Okay. I'm going to stick with you here. Plus. All right. Annika, what is the derivative of secant of a bundle of sticks? Look at the sheet. Do you have the sheet? Look it up. What is the derivative of secant of a bundle of sticks? Secant x tangent x. So what is the derivative of secant of a bundle of sticks? Secant of a bundle of sticks times tangent of a bundle of sticks, right? Okay, so I'm going to write that down. Secant of a bundle, wait, I don't write that, I write 4x, don't I? And then tangent of 4x again, right? So that's what you said. You said derivative of the secant of a bundle of sticks is secant of a bundle of sticks, tangent of a bundle of sticks. All right, are you done with the chain rule on this? What do you need still? You need the derivative of the sticks, right? Tacked on, chain to the end. So times derivative of 4x, which is 4. And are you done with the product? No, you still have this x right here. So that gets tacked on to the end. Okay, so this was like sticks. Derivative of secant of sticks was secant sticks, tangent sticks, right? So we've taken care of the secant. Now we go inside and take derivative of this. Derivative of 4x is 4, and that's tacked on to the outside. Now I don't need parentheses around the 4 because it's a single term. Had this turned out to be more than just 4, then you would have to have parentheses. That's it. So you're asking me about if the one in the book, I guess, is they have a k here. They have a k here instead of 4. So k there is considered to be a constant. It's like 4, but it's k. So how would that change our problem? We would have that would be k. This would be k. This would be k, and that would be k. So you have constants within your answer.
So is that the answer?
This would be the answer, yes. The derivatives of compositions and stuff are going to look, they're going to be complicated. Okay, let's do another one. All right. So I'm not trying to torture you. This is very similar to a problem in the book. Danielle? There you go. Okay. Are you following this okay? All right, so what do you see, Danielle? Okay, so you see like several layers of composition happening, and then inside there you see a product? Yes, is that what I heard? So if you see like mostly composition, what would be your outer function then? Cosine, right? Everyone agree? Cosine of the square root of sine of a product. Okay, so let's start from the outside and work our way in, right? Start taking the derivative. So I'll let you get the first layer. negative sine of what? Square root of sine of x tangent x. And that's it, right? I mean, that's the beginning. I just wanted you to do the outside layer, yes? Everyone follow that? That's basically Danielle doing, see, Danielle doesn't look like she wants to do this childish game of covering this up and saying, what's the derivative of cosine of the tau, right? Derivative of cosine of the tau is negative sine of the tau. Now we move on, times. So who's got the next layer in? David. David M?
He's not here today.
Not here? Did I call Ian already? I didn't. I don't know how these are getting mixed up. David G. Okay. All right, David G. What do you got, David G? What's the next layer in? We've taken care of cosine, right? So what's the next layer in?
Would it be 1/2 to square root sine?
Yeah, so now you're working on the square root part, right? So we've got to take the derivative of square root of something, which is, can I write it this way? 1/2 roots. Okay, now what goes in here, David?
Sine x, and then in parentheses x tangent x.
Y'all agree? Is that the next layer in? It is, okay? So now we've taken care of this part. Jackson, next part.
Cosine of x tangent x.
Cosine of x tangent x. That takes care of the sine part. One more piece. Elijah.
Product rule.
Product rule, good. So we are finally to the very inside, and we have, oh, there it is. We have a product right there, don't we? So product rule says we take derivative of this, right? 1 times that. So we're just going to have tan x. Is it plus or minus now? Plus. Now I'm going to start my parentheses there. Secant squared x. And then times the x. So that's my product rule. Derivative of this times this plus derivative of this times this. And I can move that, I heard someone say, I can move that x right on this right here. I can move it out here, but can't put it inside. There it is, that pretty thing right there. That's your derivative.
With parentheses.
With parentheses, have to, yep.
Where did you get the cosine x?
I didn't do it. I think Jackson did that. So where'd you get that, Jackson?
It's because the sign that's inside the radical, you take the derivative and the derivative of the sign.
Right. So what we're doing, we're working our way from the outside in. We start with the outer one, cosine. Derivative of cosine is negative sine of everything that was there. We've done this cosine, so now we go to the square root. Derivative of the square root of something is 1/2 times square root of that something. That means this stuff inside. We've done the square root. Now Jackson got this one, sine of this, right? So he said derivative of sine of something is cosine of that something. So we're done with sine. Now we get to here. Elijah's like product rule, boom. Tacking them all together with multiplication. Okay, so on this problem, that was it, right? Like that? Do y'all see what I mean by we would not want to, like big picture? See, this is composition. F, the outer function, G, H, J. Then go take the derivatives of each one and then start building out the chain rule that way. Yes, you could do it, and maybe you're one of those students that are like, this makes the most sense to me. Okay, but eventually you have to let this go. Like eventually You have to move to a place where you can just take the derivative more visually, piece by piece. All right, so how do you think you get good at chain rule? You have to do many, many, many problems. And even then, it's not enough. So I believe, hopefully, your homework assignment for chain rule is every problem there. Let's see. It's pretty much every problem there. Like if I were you, and this was the first time I had ever seen chain rule, I would try and do numbers 1 through 46, every single one of them. I would try and do every problem. And I know some of those are even and you can't check your answer in the book, but this section right here will require that you use every rule we've learned, right? You're going to need power rule in there. You're going to need product rule, and you're going to need quotient rule. You're going to need to be able to organize the order in which things happen. So practice, practice. Today is officially our first day we're supposed to be starting chain rule next class. So we're going to do nothing but chain rule next class. At least the first hour and 20 minutes. I would like to come in here and give you like a handout of chain rule problems and see if you can do them. No, not as a grade, just as an exercise. But your job is between now and then is to practice. All right, don't come in here cold, like not even having done any of the homework. All right, everyone, have a great day.
Yeah, 2.3.
Why is that like that?
Sir,
It's really weird.
apologize
For what?
for that homework.